When we pick up in section 2 of the video notes here, we have a handful of terms referring to things inside or on a triangle. The first one is an altitude. Now an altitude is a side or a segment that drops down from one of the corners and forms a right angle with one of the sides. So it is a segment and it touches the corner, touches the vertex, one of the vertices of the triangle, and it also is perpendicular to the side across from it. So it touches the vertex, it is perpendicular to the side across from it. And the reason that we most often use altitudes when you think back to very basic math, very basic geometry, is when we're trying to find the height of a triangle and we multiply base times height. We might have the base here and the altitude is what helps us get the height. Sometimes that happens outside of a triangle, like in that example there. Sometimes we would take base times the height, and the height is actually inside the triangle. But we always need something to be perpendicular, so that's where that gets used most often. Next one is a median. A median is a segment that goes from the vertice, the corner of the triangle, to the midpoint of the opposite side. So we'll see in a lot of other types of problems we'll use a median to connect a midpoint to the opposite side. Segment from vertex to midpoint of opposite side. Our next couple terms are review. We are going to go back and look at bisectors. Now bisectors cut things in half. When we have a bisector to an angle, it cuts the angle into two smaller angles. Two smaller angles, each is half. So, for example, this bisector right here, BX, is cutting angle CBA into two equal angles. One of them here, CBX, the other one, ABX. So those two angles are each equal to each other and they are each half of the original measure. Same idea when we get down to a bisector to a segment. So something that cuts through a segment here. This is going to be the bisector, the one doing the cutting, and it breaks it into two equal pieces. So AM and MB are both equally sized, and each of them is half of the whole, half of the AB. So cuts side or segment into two smaller segments. So same definition as above almost, except we're talking about segments instead of angles. And that's why it shares the same name. They're called bisectors either way. You'll notice that bisectors are always going to be lines or line segments. They are never going to be angles themselves. However, you can cut an angle or you can cut a segment with a bisector. Now building on that, we have a new one, a perpendicular bisector. It's just like a bisector to a segment. It takes a segment and it slices it in half. Now when it slices it in half, you'll notice that it doesn't just come in at any angle and hit the midpoint of that line. It actually comes in specifically at a 90-degree angle. That's what makes it perpendicular. So segment bisector that is perpendicular. upside down T, perpendicular to the segment it cuts. Perpendicular to the segment it cuts. Now, the perpendicular bisector theorem is kind of a fancy extension to just any old perpendicular bisector. If you know that this here is being bisected by this guy here, what you know is that it cuts it in half. Now, if you know if it's a perpendicular bisector, you also know that you have these as right angles. But what's really extra neat about this is that this side and this side, if they both come from the endpoints here and go to the same, meet up at the same spot up on top, these sides are also going to be equal to one another. And these angles out here are going to be equal to one another. And these angles up here are going to be equal to one another. Pretty crazy. So what I would say, instead of trying to memorize all of the separate things that are true about perpendicular bisectors, is that whenever you have a perpendicular bisector and you form two triangles like this, the midline here, the bisector itself, forms a mirror. Everything that's true over here is the same over here. The angle over here, angle over here, angle over here, angle over here, side over here, side over here, side over here, side over here. So a perpendicular bisector forms a mirror of that triangle. So let's just say as our rule, triangle is mirrored over a perpendicular bisector. And we'll just remind ourselves that's true for angles and sides. So everything is the same on either side of that mirror down the middle. Next one is a midsegment. Now a midsegment is a line, a segment here, that is connecting the midpoint on one side and the midpoint on another. So segment that connects two midpoints on sides of a triangle. And if you sound out the word, if you forget what a midsegment is, just think about what it is. Mid, so it's talking about midpoints. Segment, it is a segment. So a midsegment is exactly what it sounds like. Now, one of the things that's particularly cool about midsegments is that it has a handful of extra properties. So kind of like the perpendicular bisector makes magic happen, when you know you have a midsegment, you get that this side must be split in half, right? Because this is a midpoint. And in the same way, if this is a midpoint, this side must be split in half. Also, one of the things that's kind of neat is when that happens, you also get parallel lines. This midsegment will always be parallel to the base that it doesn't touch. So it touches two of the sides because it's touching their midpoints, and then it is parallel to this. Now, thinking of our parallel rules above, I don't want you to write this right now, but this is just something you can think about. You also get some angles that are the same. So if you think of corresponding angles here, those angles are going to be the same, or these angles here are going to be the same. So you'll get some angles that match up nicely, which can help you on some problems as well. Finally, last one we're going to look at is the triangle inequality theorem. Now I'm going to quickly describe what's actually happening here and then tell you the shortcut to this rule. So we know that a triangle has, and you don't need to write this part, you can just kind of listen along. A triangle has three angles, and those three angles always add up to 180 degrees. So if we have x plus y plus z, those are our three angles of our triangle, x plus y plus z is going to equal 180 degrees every single time. We also know that when we have a straight line, we have two angles. Let's say this is Z still just before, and now we add W over here. Whenever we have two angles together that are sitting on a straight line, they're also going to add up to 180 degrees. So we can say that W plus Z equals 180 degrees. Both of those statements are true. X, Y, and Z together, W and Z together, both of them are 180. Now, if you forget any logic here, just do some very straightforward substitution. They're both equal to 180. So I'm going to say that this must be equal to this. If they're both equal to 180, they're equal to each other. X plus Y plus Z equals W plus Z. And if I subtract Z from both sides, I get that X plus Y equals W. All I did was some algebra. I made two true statements, did some substitution, did some subtraction, and made a new true statement. X plus Y is W. And that's what the triangle inequality theorem is. It says that this angle here, in this problem, it happens to be called angle A. So we're just going to say angle A plus this one here, angle B, is equal to what is called angle C here, this outside one. So the two inside angles, in the picture below I called it X and Y, is equal to, when you add them up, W, the outside one. And that's what we found to be true, and we just did some algebra down here. So the reason that this triangle inequality theorem works is simply by taking these statements and doing a little bit of algebra with it, but just so that you have a shortcut whenever you see two interior angles and the other exterior one, so not the one next to the exterior, but this one being blank here, you don't even need to know what that is. It's irrelevant. As long as you know these two interior and this third exterior, you can form a true statement, which will help you solve a bunch of problems as well.